So let's discuss allowed values of angular momentum J. So what are all the values allowed for a given angular momentum? So that one we would see. So since Jz and J square commute, they will have a set of simultaneous eigenvectors and therefore can be simultaneously diagonalized. So as we know that the commutation of from the commutation relations where we have commutation of j square and jz, and commutation of jz comma j square or commutation of j square comma jz is nothing but 0. So that is nothing but j square and jz commute with each other. So because of that commutation, they are said to have simultaneous eigenvectors. J square and Jz are said to have simultaneous eigenvectors. That means same eigenvectors, and which can be diagonalized simultaneously. So eigenvectors can be because of which these two can be Jz and J square can be diagonalized. So let the basic vectors in the representation in which j square and jz are simultaneously diagonal be psi of lambda m will satisfy. So both of them must be diagonalized simultaneously. That means that wave function must be a function for, so the function which we decide, it should be stand as an eigenfunction for both of them simultaneously. It should be a wave function of this, and it should also be a wave function of this. So a given wave function is called as a wave function of particular operator if only if it gives a, if that operator operates on that wave function and again it gives the same function multiplied with its eigenvalue. So that is the case. So that one we need to, that one we are assuming to be psi of lambda m. So psi is a function of lambda and m. Y means you can see here. So when j square is operating on that eigen function, it is that is I of lambda m, it is giving us the same eigen function multiplied with some constant, that is this is called as eigenvalue. So j square's eigenvalue is lambda. In the same manner, when jz is operating on this same wave function psi of lambda m, it is giving the same wave function multiplied by its eigenvalue, that is small m. So we can say that this eigenfunction, this is the eigenfunction for this j square as well as jz. So at the same time, so with respect to j square, its eigenvalue is lambda, and with respect to jz, eigenvalue is m. So that's why xi is a function considered as a function of lambda and m, where lambda and m are real numbers. So here lambda and m are considered to be real numbers. J square and jz are Hermitian. J square and Jz are Hermitian means if A transpose conjugate is equals to A, then that is called as Hermitian. So any operator can be called as a Hermitian if we take the conjugate of that particular eigenvector or operator, and if we do the transpose of that, then we would get the same operator. That is suppose if we take a matrix, A is a matrix, if we take the transpose of that matrix and again conjugate of that matrix, we would get the same matrix as before. So that is nothing but Hermitian. So we will use commutation relations to determine the eigenvalue lambda and m. We use the operators. So now we need to find out what are these eigenvalue. What could be these eigenvalues? So we determine the eigenvalues lambda and m. So we use operators. So we are using j plus operator. J plus is nothing but jx plus ijy. In the same manner, next j minus. J minus is nothing but jx minus ijy. So if we see here, j plus dagger is nothing but j minus. That means if we consider the conjugate, complex conjugate as well as transpose. So first of all, if we consider the complex conjugate of this one, here we are having jx plus ijy. Its complex conjugate is nothing but minus. In the place of plus I, we would have minus I. That is nothing but this. Jx would be jx as usual, plus ijy would be minus ijy. So j plus dagger complex conjugate is nothing but j minus. which satisfy the commutation rules. So this j plus j minus would satisfy these commutation rules. So let's have a look at these commutation rules. So j plus commutation of j plus comma jz, as we already know that j plus is nothing but jx plus ijy, and as we know that a plus b, that is a plus b comma c conjugation is nothing but a comma c, that is sorry, commutation. So a, so sorry, b comma c, so a comma c plus b comma c, so distributive. So hence we are having j, first of all jx jz, because jx jz combination, and again we are having ijy. So I, if it is taken outside, jy jz, and as we know that commutation of jx comma jz is minus I h cut jy, actually xyz has to come. So if there is jz comma jx commutation, then we would have got I h cut jy. But this is jx comma jz. So we need to go in cyclic manner, x, y, y, z, zx. So I h cut jy. And here if we are taking h cut to be 1 unit. So for to make simplification easy, calculation easy, h cut is taken as 1 unit. So we in the place of h cut 1. So minus I h cut jy is nothing but minus I jy. And here also j commutation of jy jz is there. So we need to go in cyclic manner, x, y, y, z. So y, z, so which is missing is jx term is missing. So I h cut jx we would have. So it is in cyclic order. So commutation of jy jz is jx, I h cut jx. But h cut is 1 and I into I is nothing but minus 1. Hence we are having minus jx. So overall if we see, if we could take minus as common, we would get jx plus ijy, that is j plus. So thus the commutation of j plus jz is minus j plus. In the same manner, if we proceed, if we do j minus jz commutation, we would get j minus equal to j minus. So how means substituting in the place of j minus jx minus ijy and applying commutation rules, again we would get this. In the same manner, if we do commutation of j plus comma j minus, we would get 2jz. So here distributive law we need to follow. Here we would have jx plus ijy, here we would have jx minus ijy. So distributive form, that means a plus b comma c plus d, like that form we would be having. So we need to apply separate distributive form. So in that we would get 2jz. We follow the same procedure. And identities. So now if we do the product of j plus and j minus, so j plus jx plus ijy, jx minus ijy, jx into jx, jx square, and ijy into minus ijy, so minus I square jy square. So minus I square jy square, I square is nothing but minus 1. So minus into minus plus jy square. And next thing is, and jx into minus ijy, that is minus ijx jy. So minus I, another thing is I into jy jx plus I jy jx. So if we could take minus I as the common in that product, so we would get so minus I is taken as common, jx into jy, and here so minus jy jx, that is nothing but jx comma commutation of jx comma jy. As we know that commutation of a comma b is nothing but ab minus ba. So based on that we would have, so minus I if you would take common, the simplification. And next thing is, again we know that commutation of jx comma jy is I h cut jz. H cut is taken as 1. So I into I is I square minus 1, minus into minus plus. So plus jz we would have. H cut is taken as 1. I h cut jz is, so we would have this. And next thing is jx square plus jy square can be written as, so actually j square is nothing but jx square plus jy square plus jz square. So if we send jz to this side, so j square minus jz square is nothing but jx square plus jy square, like that. So this is the formula for j plus into j minus. In the same manner, if we multiply j minus into j plus, here actually this is j plus into j minus. So it is of the form AB. This is BA. So as we know, AB is not always equal to BA. Even in the matrices we could have gone through. So here in the same manner, this is not equal, AB is not equal to BA. In the case of operators also, this is the same. So j minus into j plus, if we do calculation, we would get j square minus jz square minus jz. And next, now consider the scalar product. So if we consider the scalar product, so xi j square xi, so j square operating on the wave function and again multiply with that wave function, like that. So j square can be written as jx square plus jy square plus jz square. So we are just distributing this, and this could be written as this. So here jx square is there, we are just distributing it. So as jx, jy, jz are Hermitian, because of that Hermitian property, by the property of Hermitian, we could have this. So jx square, so j square operating on wave function and again multiplied with wave function could be splitted up as jx operating on that wave function, again jx operating on that wave function, again product, scalar product. So this could be written in this form. In the same manner, this also jy square operating on wave function. So this also could be splitted up like this, jy square. So jy operating on wave function, jy operating on wave function, and their scalar product. So here also the same thing follows. Jz square is splitted up in this manner, and we know that this is greater than or equal to jz of xi, jz of xi. So just like a plus b plus c is greater than or equal to c. So because here c is already existing, so if we suppose a plus b plus c is greater than or equal to c, what is the meaning means, if we consider a and b are 0, then c is equal to c. So hence here we are having equal to sign, this equal to this. And if c is if a and b are some positive terms, so c is added with these positive terms, so the value of c would increase. So hence this is greater than this, that is a plus b plus c is greater than c. So from that we are getting this. So as for any vector, x is greater than or equal to 0, because for the vectors this scalar product is greater than or equal to 0, and substituting xi equals xi of lambda m we have. So in the place of here, in the place of xi we need to substitute xi of lambda m. So here xi of lambda m, here xi of lambda m. So this is greater than or equal to jz into xi of lambda m, jz into xi of lambda m. So using equations 1 and 2 we have, that means this is equation 1 and 2. So j square operating on wave function would give eigenvalue lambda multiplied with this eigenfunction. Here also jz operating on this eigenfunction would give us m, and again the same wave function. So from the eigenvalues here also the same. And here if we see here m common, here also m common. So m into m, two m's are there. So m into m, m square. So overall lambda is greater than or equal to m square. So this is the important condition for finding the allowed values of angular momentum. So this is very important condition, lambda is greater than or equal to m square. So now from equation 6, so this is equation 6, j plus jz commutation. So we are having minus j plus, so this is that j plus jz commutation. We know that the commutation of AB is nothing, AB minus BA. So that is j plus into jz minus jz into j plus. So operating on eigenfunction we have. So now what we have to do is operating this operator form are to be operated on wave function, operating with wave function. So if we do that means if you just like if we are multiplying with wave functions on both sides, like that. So we are making these operators to operate on wave functions xi of lambda m. So if this is operating, we would have j plus jz xi of lambda m, and j minus j plus xi of lambda m, and here also the same thing. And next here what we have to do is we need to send this minus j plus this side. So here it is minus, so if we send it this side, it would add up. So j plus jz xi of lambda m plus j plus xi of lambda m, and this one has to be sent to this side. So here minus is there, so if it goes to that side, plus. So plus jz j plus xi of lambda m. And now when jz is operating on this wave function, we would have m xi, m into xi of lambda m, and j plus into xi of lambda m as usual. And here what we see is j plus xi of lambda m. Here also j, here this is a constant, could be taken out. So here also j plus xi of lambda m, here also j plus xi of lambda m. So if we take it as common, what would remain is m. Here is 1, so m plus 1 j plus xi of lambda m. So overall if we see, so jz is operating on this wave function, and it is giving the same wave function multiplied with its eigenvalue m plus 1. So in addition to xi of lambda m, not only xi of lambda m, from this equation, what does this equation tell us? So xi of lambda m is a eigenfunction of this operator with eigenvalue m. And what does this equation tells us is j plus xi of lambda m is an eigenfunction of this jz operator with an eigenvalue m plus 1. So that is the meaning of this equation. So if xi of lambda m is a wave function of jz operator, then j plus into xi of lambda m is also an eigenfunction of jz operator, and its eigenvalue is m plus 1. Just we have for xi of lambda m eigenvalue m, here it is m plus 1. And next thing is commutation of j square j plus equals to 0, because we know that j plus is nothing but jx plus ijy, and j square commutes with all jx, jy and jz. You can see the refer to the commutation relations. So from that we have j square commutes with jx, jy, jz, like that. So if we apply distributive law, so j square operating on jx plus I into j square jy, so their commutation would be 0. And we know that j square j plus ab minus ba could depend as ab minus ba. So j square j plus is equals j plus j square, and operating with the wave function on both sides. So xi of lambda m, here also xi of lambda m. So j square operating on this wave function would give us lambda. So j square operating on wave function, it would give us eigenvalue lambda on that wave function. So here if we observe finally, so j square operating on this wave function, that is j plus xi of lambda m, it is giving us the same wave function, that is j plus into xi of lambda m. So here this is the wave function. So initially we have taken xi of lambda m as the wave function. Here j plus into xi of lambda m is taken as wave function. So j square operating on this wave function giving us the same wave function multiplied by its eigenvalue lambda. So this is also an eigenfunction of j square. So these two conclusions can be drawn. So here we can see it. So it is clear from equations 13 and 14 that eigenvector j plus xi of lambda m is an eigenvector of jz belonging to the eigenvalue m plus 1. So it is an eigenvector of jz belonging to eigenvalue m plus 1, and of j square belonging to the same eigenvalue lambda of j square. So it is also an eigenfunction for this j square belonging to the same eigenvalue lambda, just as we have eigenvalue lambda for xi of lambda m. So here the eigenvalue is not changing, so it's remaining the same for j square. Only for jz it is changing. So similarly j plus into j plus xi of lambda m. So first operating j plus on this wave function and again operating j plus is also an eigenvector of jz, and it belongs to eigenvalue m plus 2. So in this manner the m value goes on increasing by 1, and of j square belonging to the same eigenvalue lambda. So it is also an eigenvalue of j square belonging, and again the same would repeat. Here also we would get the eigenvalue lambda. So this process cannot continue indefinitely, otherwise it will contradict equation 12. So what equation 12 this? So this is very important. So this process cannot be keep going, and so because lambda is greater than or equal to m square. So it would be satisfied. So suppose let us suppose lambda is 9. So if we take 1 square, so 9 is greater than 1 square. And if we take 2 square, so 9 is greater than 2 square. And if we take m value 3, so 9 is equal to 9. And if we take m value, if we keep on increasing m value, 1, 2, 3, now 4. So 9 cannot be considered as greater than or equal to 16. So at certain stage this must end. So that is the thing they are saying. So this process cannot continue indefinitely, otherwise it will contradict equation 12. And let mu be the greatest eigenvalue of jz for the given eigenvalue lambda of j square, and psi of lambda mu be the corresponding eigenvector. So there would be some particular greatest value. Just now as we have considered, lambda has 9 and m value 1, 2, 1 square, 1, 2 square, 4, 3 square, 9. So yeah, that is the maximum possible value. So beyond that 4 we cannot take. So that is, so here also we are need to consider. So give we need to consider mu is the greatest eigenvalue of jz. We need to consider in such a manner. So then what we would have is under jz for a given eigenvalue lambda of corresponding wave vector. So now if we consider jz operating on j plus into psi of lambda m, so it would give us the same j plus psi of lambda m, but here eigenvalue is m plus 1, that is mu plus 1 in the but j plus psi of lambda m must be 0. Why means we cannot have, as m value we have reached maximum m value already, we have taken mu has to be the maximum m value. So in the case of 9 is greater than or equal to 3 square, so there 3 is the maximum value. So 3 plus 1 4 is not allowed, hence this must for a wave function must not exist. So hence it must be equal to 0. Hence j plus into psi of lambda m is equals to 0. The meaning of this is that m value cannot be increased to further. So j plus operating on wave function, what does it do? It increases the value of m by 1 unit. So but if it increases, it would dissatisfy the 12th equation, that is lambda must be greater than or equal to m square. Hence this is equal to 0 for maximum m value. And since mu plus 1 cannot be an eigenvalue of jz, so thus we have as j plus psi of lambda mu is 0, operating with j minus on both sides. For this equation we would get this equation, so that also would be equal to 0. But from j minus into j plus, so here we have already j minus into j plus, so this is the value. So j square minus jz square minus jz. And next what we have to do is we just need to split it up. So it is of the form a plus b plus c into d. So AD plus BD plus CD, like that. So j square operating on this wave function would give us the same wave function multiplied by its eigenvalue lambda. Eigenvalue of j square is lambda. The same with jz operating on wave function 2 times. So for one time it would give mu, for another time mu square. So mu square. And again jz operating on the wave function, it would give us 1 mu psi of lambda mu into psi of lambda mu. So that is the thing. So if it is taken as common, we would have this form after simplification. But psi of lambda m is not identically 0. Hence mu is the root of the quadratic equation, larger root of this equation. So here it is of the form ab equals to 0. Then either a equals to 0 or b equals to 0. But if this wave function is considered as 0, then the wave function does not exist. So if the wave function does not exist, then what is the meaning of operating j plus on that wave function, j square on that wave function? So the wave function must exist. So only possibility is this term must be equal to 0. So if we see here, it is of the quadratic form in mu. So x square plus ax square plus bx plus c, like that. So here x in the place of x square we are having mu square. So mu is the root of this equation. So this could be written as this, just multiplying with minus. So minus lambda plus mu square plus mu. So here if we compare with ax square plus bx plus c, like that form. So here in the place of a we are having 1, here in the place of b 1, here in the place of c minus lambda. So again we know that root of the equation is nothing but minus b plus or minus root of b square minus 4ac by 2a. So if we just apply, so minus b means minus 1. So minus 1 plus or minus plus root over b square means 1. 1 minus 4ac. 4 1 into minus lambda. So plus lambda. 1 plus 4 lambda you would be having by 2a. 2 into 1. 2. Hence this is the equation, but here they are saying larger root of this equation because we have considered mu to be largest number, largest possible number, satisfying lambda greater than mu square. Lambda must be greater than mu square, that equation. So as we are considering largest possible number, so we need to consider plus sign. That's why we have taken only plus sign. So plus 1. So minus 1 plus root of 1 plus 4 lambda by 2 we would get. So we just after simplification we get this. So this is the form. And next, similarly, jz operating on j minus xi of lambda m. So just we have jz j minus. So this from this commutation rule, j minus jz. So j minus jz minus jz j minus is equals to j minus. So based on that commutation rule, we would have this. On simplification of that commutation rule, from that commutation rule, we would have this form. And again multiplying with xi of lambda m on both sides, we will get this. And here if we see jz operating on this wave function, m into xi of lambda m. So j minus xi of lambda m, j minus xi of lambda m could be taken as common. So m minus 1, you would have m minus 1. So j square operating on j minus would give us 0. So they commute with each other. So hence j square into j minus is equals to j minus into j square. So from that operating with wave function on both sides, so j square operating on this wave function would give us the same wave function multiplied with its eigenvalue, and j minus is also there. So from these two equation again the same. So jz operator's eigenfunction is this with eigenvalue m minus 1, and j square's eigenfunction is this. This is also an eigenfunction of j square, j minus into xi of lambda m with its eigenvalue lambda. So that's same thing. So it is clear from equation that the eigenvector is an eigenvector of jz belonging. So just we have discussed now. So eigenvalue m minus 1 and of j square belonging the same eigenvalue lambda of j square, unless of course if j minus xi of lambda m equals to 0. So repeated application shows that j minus xi of lambda m is an eigenvector of jz belonging to the eigenvalue m minus 2. That means first we are operating one time, we are operating j minus on xi of lambda m, and again second time also we are operating j minus on this wave function. So hence we are having m minus 2. So this cannot continue indefinitely, otherwise it will again contradict equation 12. So this process cannot continue indefinitely. So if we cannot go on reducing the value of m. So hence because it would again contradict this equation lambda greater than or equal to m square. So it would contradict that term. So that one they are saying. So if mu1 is the least eigenvalue of jz. So if let us consider mu1 is the least possible eigenvalue of jz, then we would have j minus into xi of lambda mu1 equals to 0, because we cannot further reduce the value of mu1 by 1. Already we have reached. So for 9 greater than or equal to m square, so minus 3 whole square is nothing but 9. So beyond that we cannot go. Minus 3 whole square is nothing but 9, and minus 4 is whole square is 16. So it must stop at minus 3 itself. So what does this do? It decreases the value of m by 1. Minus 3 minus 1 minus 4 is not acceptable. Hence this is equal to 0. And next, operating with j plus on both sides for this equation, we would have this. And as we have already derived this j plus into j minus formula. So j square minus jz square plus jz entire thing equals to 0. And again the same. we need to just distribute this. J square operating on wave function would give us same wave function with the eigenvalue lambda, and Jz operating on xi two times. Here it is operating on one time. So Jz operating on wave function could give mu1 into xi of lambda mu1. Here two times. So mu1 into mu1 whole square. So one time mu1, another time into mu1 into xi of lambda m. So mu into mu1 square. So this is again of the form AB equals to 0. So either A equals 0 or B equals to 0. So this wave function cannot be 0, cannot be equal to 0. Then it won't exist. So this is equals to 0. So here if we multiply with minus for so that x square we would have plus x square mu1 square. So mu1 square minus mu1 minus lambda equals to 0. So it is a quadratic equation in terms of mu1. So if we find apply the square root formula comparison, if we do a value, b value, c value, and if we apply this formula, from that we would get this. So actually the smaller root of the above equation means we have plus or minus square root of b square minus 4ac. So in case of largest root, what we have done, we have taken plus sign, because it only if it gets added up it could get maximum positive value, and here smallest root, hence we are taking minus sign. So we can get negative value, minimum possible negative value. Thus mu1 is equals to minus mu. So from this if we see, mu1 is plus half but mu is minus half, and mu1 is minus half root over 1 plus 4 lambda. Here it is plus half root over 1 plus 4 lambda. So only difference is minus sign. So mu1 could be written as minus mu. So that is the thing. Just like 9 is greater than or equal to m square. So 9 is greater than or equal to 3 square. At the same time 9 is greater than or equal to minus 3 square also. So plus 3 square as well as minus 3 square. And the eigenvalues of Jz are. So eigenvalues of Jz are starting from minus mu plus 1 and ending. So taking maximum positive value and minimum negative value. So maximum positive value is mu as we have found here, and minimum negative value is this mu1, that is minus mu. So in between them, so we can reduce. So from this we can come to this by operating j minus. So it will reduce the value of m by 1. So mu minus 1, again mu minus 2, mu minus 3, like that. And finally if we go on reducing, keep on reducing, finally we will achieve minus mu, that is 3 minus 1 2, 2 minus 1 1, 1 minus 1 0, 0 minus 1 minus 1, minus 1 minus 1 minus 2, minus 2 minus 1 minus 3, like that. So it follows that 2 mu must be an integer. That means multiplying with 2 on both sides, you get 2 mu minus 1 plus root of 1 plus 4 lambda. So it could be as an integral form. So that one they are saying. So it follows that 2 mu must be an integer, and 2 mu is equals to, in that integer is n, and mu is equals to n by 2, and n value starts from 0 1 2 3, like that. So now in the place of mu we replace with n by 2. So in this equation n by 2 plus minus half plus half root over 4 1 plus 4 lambda. So we have replaced with n by 2. Now if we do rearranging, so here we have given, so sending this minus half that side, so n plus half, n by 2 plus half, that is n plus 1 by 2, and 2 would get cancelled, and squaring on both sides we would get this, and n plus 1 whole square is nothing but n square plus 2n plus 1. So 1 would get cancelled, we would have this, dividing by 4 we would have n square by 4 plus n by 2. So if we n square by 4 is nothing but n by 2 whole square. So if we could take n by 2 common, so n by 2 into n by 2 plus 1, n by 2 into n by 2 plus 1. So that is the simplification procedure lambda. So lambda is equal to j into j plus 1, and j is 0 half 1 3 by 2. Why means j is nothing but n by 2. N is nothing but 0. 0 by 2 is 0. 1 by 2 is 1 by 2. 2 by 2 is 1. And 3 by 2 is 3 by 2. We would have. So from this. So lambda equals j into j plus 1. So the value of lambda is j into j plus 1. Hence we have eigenvalue of j square has j into j plus 1 h cut square. So the eigenvalues of the operator j square are the numbers j into j plus 1, and where j is equals 0, half, 1, 3 by 2, and each of this is 2j plus 1 fold degenerate. So just we have L values. It would have 2L plus 1 m possible m values. For a given L value, there are 2L plus 1 possible m values. So that is the thing they are saying. So 2j plus 1 fold degenerate. The eigenvalues of jz for a given value of j being the eigenvalues of jz for a given value of j. So the eigenvalues of jz for a given value of j is nothing but this. So that eigenvalues of jz are nothing but m h cut, that is m for a given value of j. So those eigenvalues, that is m values, are this. So ranging from minus j to plus j with a difference of 1. So minus j plus 1, minus j plus 2, and so on, j minus 1 j. So maximum value is j and minimum value is minus j. So if we had not chosen the system of units, we would have obtained j as the eigenvalue of. So here actually what we have done here is we have taken h cut is equals to 1. So if we have not taken in such a manner, then we would have got j into j plus 1 h cut square. So actually this is h cut square as the eigenvalue of j square, and minus j h cut minus j plus 1 h cut j h cut as the eigenvalues of jz. So just like eigenvalue of Lz is m h cut. So here h cut is missing. Why means at the starting we have taken h cut is equals to 1. So these are the allowed values of angular momentum j, ranging from minus j to plus j. So thank you.